We started the design competition on this job with the owner Greenland from Shanghai a couple of years ago. And it was a very fiercely competed design among a lot of top-rated architectural firms around the world. So we, Thornton, Tomasetti, and the Adrian Smith architects were the third team to be interviewed. When we walked into the interview room, we saw the two models presented by our competitors. So our hearts sank right away because their scheme are much more straightforward and simple. If you look at the shape of this tower, it is quite complex when you look at the exterior shape. Well, first of all, this project is located in Sichuan province, the provincial capital of Sichuan province along the Yangtze River. It is a city of 14 million population, and the city is surrounded by hilly mountains and snow-capped mountains. So Adrian Smith architect, designer, took the inspiration, the snow-capped mountain, represent some kinds of crystal, ice crystal. And then the valleys and the ridges of the building represented by the valley and the slopes of the mountains. That's how they present their architectural inspiration to this landmark tower. But it really creates a challenge to us and also to the contractor when they first look at it. They all immediately ask us a lot of questions about the cost and the efficiency of this building with this multiple facet exterior shape. And if you look closer, you can see not a single plane in the exterior is similar, and it's quite complex. Too bad I already submitted our fee proposal. We cannot change it. That's what we committed to do. And the last thing we want to tell the owner is make sure that this is very efficient. Don't worry, we can get it done. Structural is not a problem. Basically, we did work out a very effective structural system before the design competition, and we are very confident that this will be one of the actually very efficient building when we can make full use of what the architect has given us. So we try to turn the difficulties into a very good situation for us. So the building is 468 meters tall, 101 story, mixed use with office and suites and hotel. That means when you have the hotel on the top, you have to make sure the building will satisfy a more stringent acceleration criteria. That's not like an office. Office, you can go up to 25 milli-G, but hotel, you have to scale it down to at least 15 to 20 milli-G to make it more comfortable. And also the tower crown, we will also be asked to, maybe the building will increase to 500 meters tall. So I say we have to increase the fees again. So they keep it low. Look at the other two buildings. We also have to design two adjacent buildings, 167 meters tall and 170-something meters tall residential tower with a podium. So nothing is easy. Again, everything has to mirror each other with the same, it's the same theme. So this is the ridge, this is the valley. So how do we make it happen? So normally, when we did the Chicago building, we try to push the column in order to cantilever the slab and so on, in order to free up the facet. You can do all kinds of variation for the actual slab to accomplish that. But when we try that, it won't work because it will take up too much interior space. So we'll go into detail. And also, each floor, everything is different. And if you try to push in all the columns to the very inside space, it will just kill all the interior room, and you end up to have a huge cantilever floor. So we rule out that scheme. And also fabrication will be a problem because all the floor beams will be varying so much, and we'll have an upheaval by the contractor. So we try to simplify it as much as possible. Now, the base of the building is about, it's about 65 meters. And it tapers up to about 43 meters. And we have around 16 perimeter column around. So we decided to push the column all the way out in order to deal with this geometry. And this is one of its kind for a 100-story building with column not being straight. Usually when you have a tower, you try to keep the column straight up, straight down, or try to slope it up and down or transfer. But this time we have to deal with the zigzag shape of the building. And also, this is another floor plate that shows you another actual slab detail. And this is another shake up and down. So basically, in order to accommodate the shape, the column, this column is moving all the way in when this is other way in and this is out. So you have a zigzag shape column as it moves out. And in between, we'll explain to you later, in order to do that, we try to keep this shape constant so that we have a typical floor plan as much as possible so that the framing plan is identical on almost all the floor except for the length itself. Now, and in between, we'll go into the other detail, is the foundation. Before I go to the lateral system, how we make full use of this zigzag shape to our advantage. The building itself is rested on hand-dug caisson. The soil in Chengdu is pretty good. It has, when we go down around 50-something meter, we can find, or 40 meter, we can find shale or weather mud rock. But we have an incident from the original soil report. They find that the bearing capacity of the soil is only 3,500 kPa, 3,500 kPa. So we act on the belief that this is accurate, but we end up to have all this pile or caisson to basically won't fit. So we're surprised at what happened. So we asked for a peer review and then asked them to examine the testing method. And this is the extra step we took. We challenged each other, and we found that they may have used the wrong testing method. Indeed, they find they use a very small loading plate to test the bearing capacity of the soil. So immediately, we ordered them to do another loading test and try to excavate deeper to give more space for them to do a loading test for the bearing. And listen, what happened is after they test, they use a deep plate loading test, and the capacity ended up to be 7,200 kPa. There's a big difference between 3,500 kPa bearing capacity. So this is your instinct that pick up your curiosity. You cannot depend on someone telling you what it is. We challenge it, and we end up saving a lot of piles. And we end up saving the mat thickness from 6-point-something meter to 4.5 meter thick mat. So this is another exercise we go through as a structural engineer, continuing to question ourselves. Okay, going back to the facet situation of the tower, every plane is different, and every geometry is different, which is without the computer, the Rhino model, and all the computational analysis and the tools we use with the architect and engineer, it's impossible to get this geometry right. Basically, each kinking point is about 14, 16 floor, and none of them are the same plane. So we have to model it quite accurately, because if we don't model the inclination carefully, the kinking of the column creates the in-plane stress on the slab and also on the perimeter. And we have to exactly find out what kind of kinking stress is the in-plane stress with finite element analysis. So we have to be very accurate. And also for all the connection design for your spandrels and for your slab horizontal reinforcement. Now you can see how we turn the geometry into our advantage. Basically in China, for building this tall, we did a dual system. Even for IBC code, we need a dual system. So the core alone will not be sufficient enough to make this building work. So normally, like our other buildings that Mr. Kim presented, you will use a Outrigger system, an Outrigger system with a super column connected to the Outrigger system. But even that is not satisfying the China code. China code requires you an exterior, a secondary system that is giving you a stiffness almost 10%. with a minimum 20 to 25% strength for the seismic load. So immediately we will need some kind of exterior system, a frame system to satisfy the China code. So immediately with all the experience we gain in China, we know that this exterior bracing system will contribute something. But at that time, we don't know how much it is. And until we win this design competition, we work it out, and we find that this is amazingly very beneficial and efficient. So basically, the column, this red column is kinking in and out, and then in between, we introduce this mega bracing that follow the ridges of the facade. And it works out so well, and the owner is happy. It becomes part of the structural system that works with the facade, and also providing the support for the curtain wall as well as the mullion. And I do not know how many times we changed the geometry of this model in order to understand what the exact stresses are, because we have to be extremely accurate. Another thing is I don't want to name names, someone asked us to, there are 3 levels of Outrigger system. Outrigger is not a simple thing to build. It is very costly. It takes a long time to have all the connections, detail, and build it, and also go through the shear wall and everything. So we always try to limit the amount of Outriggers. So with all kinds of exercise, again, you hire a good engineer, they do more for you with more experience. We don't stop right there. So we continue to optimize the location of the outriggers, and then we try, eventually we eliminate 1. So basically we end up to have only 3 outrigger system. We save about 700 tons of steel and another month of construction. So, I know all of you are good engineers and architects. You have experienced all kinds of systems, but it is the continuous effort as an engineer to keep on chasing ourselves. Same thing, the building is tapering. It helps a lot. When the building tapers, it reduces the wind load, it cuts down vortex shedding. At the same time, the facet of the multiple facets of this building greatly reduces the wind load. So again, this is another reason we win this design competition, because the design and the structure go hand in hand. That really breaks the odds, even with such a complex geometry. So anyway, when we taper it, it poses a challenge, because if we keep the core straight up, there will not be enough efficiency for floor space upper. So how do we do it? Well, of course, you can say when we reduce the shear wall core, we can do a transfer. But it is a no-no to transfer shear wall or major lateral system in China, which they discourage. And also, there's also a structural concern also for all the seismic dynamic loading. What do? We say, okay, we try to insert, we don't want to transfer the core, so we try to taper. So we suggest to the building department and expert, we start sloping, but we try to shrink the core by sloping the exterior flanges of the core, by sloping it. So this creates another round of analysis how to slope the core. First, this is the first time in China they have ever done a 100-story building with a sloping core for the transition. So we work out, we work with the contractor if they can do the form work and the shoring and the bracing, what kind of diaphragm action we need during the transition of the floor. And we solve that problem by talking to them, working closely with them. Then the next thing is, we have to go to the expert who approve this job and review this job, whether they will accept this, because this is the first time they have done it in China. Of course, we have done it in the other part of the world. So with our broad experience and our college experience, we prove to them that it can be done. Again, we have to do more analysis every time the forces change the load path, and provide them more lateral forces component. We have to do more. So once we find the easiest system, the next thing is we know what to do to solve the problem. And this is our way to do a good job. And you see, the the core itself at the base, normally we try to simplify the core too for a building. If we can simplify the core, which is the heart of the building, you solve almost 50% of the problem or more. And how do we make the architect work? Because you can see all kinds of strange core layouts. So for us, for Thornton Tomasetti, we always work closely with the architect and the vertical transportation engineer, mechanical engineer. What is the best solution for the core? This morning, the planetary section speaker said the most efficient building will be the most profitable building. This started from structure and architecture. So we don't want the core to be V-shaped. So we always like the tic-tac-toe, which I learned when I was a kid. And the thing is, normally this corner can easily drop off and so on. So we try to keep the simple system and simple concept. So here we are. We end up, trying to convince everybody to use a very simple and isometric core with nice square because of the octagon shape of the building and the hexagonal shape of the building and the polygon shape of the building. As it goes up, we must chamfer the corners. And we're okay with that. And this corner happens to be the best location for us to knock out this corner as it goes up. But as it goes up, this web wall becomes flange wall as it goes up. So when we need certain thickness for all this flange wall at the bottom, it give us some penalty on the wet wall below. So we try to optimize the building, but we have a limitation. So at the end, we are forced to not be able to reduce the thickness of the wall too much, but we reduce the reinforcement at the bottom to compensate it since we have the space. So you balance each other and achieve the goal and not to transfer. And construction is a breeze, very fast construction, and everyone is happy. So we keep it simple and stupid, the KISS way. And again, this is a transition, and we do the transition the first in China to do that. That's another thing. They want us to transition through 15 floor and so on, but we try to compromise because every time it takes more floor to transition, it wastes architectural space. We don't want to do that. So finally, we come to a number that's reasonable with transition in 10 floor from a 28 by 28 meter core, we shrink it down to 24 by 24 meter, and everyone is happy. And at that area, the architect's happy, and we're using the mechanical floor to do most of the work. Outriggers, okay. Since we try to keep the column of uniform sizes, rather than a super column, we punish 2 columns on each side. We try to distribute the load more evenly. So we are using an outrigger on those 2 outrigger floors, every other one. So there's outrigger, every other one in order to do that. We also have the floor horizontal trusses in order to take that kinking force and all the outrigger forces. Those are the outriggers, okay. And you can see the framing plan is really, really simple, and that's a way to keep everybody happy. This is where we go, and our computer helps us to understand that. Well, we have a larger perimeter beam at the top chord and bottom chord of the outrigger system. Again, we use composite column in order to keep the column size small, and we have to adjust the reinforcement of the adjacent column, which is not working as a super column, has less wind load. So basically, we have to be careful to calculate the stress and strain relationship between each column, and also we have to understand all the stress and strain relationship between the bracing of the outrigger and all the bracing with each other, because you're not building a 30, 50-story building. When it goes up beyond 50, all these small numbers add together. We have to be very careful. So we're constantly checking this number so that we have a balanced situation. As long as we know what to do, you can avoid more trouble. This is not a rocket scientist job. Again, okay, here we go. We finish it. Again, we try to prove to the Chinese authority that the exterior frame is good because how much the core is doing for overturning moment, how much stiffness the exterior secondary frame is doing. So we bargain a little bit with them for a reason. Right now, we can prove that the frame, mega frame can give us almost about 5 to 8% of stiffness or shear, absorb so much shear into, seismic shear. So actually, they want 10%. We continue to bargain with them. Reason is that we find that, I'll show you later, the building already is quite stiff enough already. We don't want to go too far because you don't really need the exterior frame for all the stiffness. The core itself and the outrigger itself is good enough, but we still have to satisfy the local requirements. You can see when we have the big outrigger in the middle, we have about 9,000 kilonewtons of shear, but we have a -4. So if this one we subtract itself, it gave us the right number of 5,000 in this area. So this is the distribution of shear between the core wall and the exterior frame. So we continue to check ourselves. We find, it's very logic. We prove ourselves that it's a very efficient system. The core takes 60% of the overturning moment, and the outrigger system and the pyramid system take over about 60% of the overturning moment. So it is quite logical with all the high-rise beam that my colleagues and everyone has been doing. We just continue to optimize ourselves and to get achieve the best result. Advantage of the 3D exoskeleton, it is the first of its kind. I mean, you never see a building with columns, zigzag, zigzag. Nothing is in the same place. Everything is in pieces like a match, pieces. So we are very proud of ourselves and to our team that they achieved this geometric nightmare task. Basically, this new system, the exoskeleton, help us to achieve the secondary system thing, and it gives us the requirement it can take. Now, we also do extensive study on the curtain wall panels because this ridge and valley create different panel curtain walls. So we are working with Adrian Smith, architect, very closely, and we adjust so many times the slope and the dimension in and out of this in order to fit the curtain wall. Otherwise, you will have 1,000 types of curtain wall panels, so many types. So there's so many try and error in order to achieve it. What you see is so much hard work, just the labor work, I have to say that, with the right tools. It turns out to be quite simple. They can do a very simple curtain wall system. And also, we can do, this column is in and out, and the diagonal bracing is in and out. And we achieved this. There was at night, it's built. When it is built, it will be so beautiful. Thank God. When they ask us to do Tower 1 and Tower 2, we tell them, we don't want to repeat this system again unless you change our contract. So we persuade them to make it simple, and Mr. Architect, don't kill us all at one time. So we try to we make it through. Again, nothing will be done unless you tell the engineer and the contractor all the connection details like my colleagues are doing on their project. This is we do a lot of final element analysis and all the performance-based design. So these are the diagonal bracing and the steel composite steel bracing and how it works together. We show it with our Revit model or BIM model to do that. We have fundamental element models as well to prove to the expert how everything works. So this is the best thing about performance-based design. Nowadays, if you want to do the code-based design, prescriptive design, it's mainly linear. It's not applicable, it's not that useful anymore, I would say that, because we have the tools to do performance-based design already, except that you need the interpretation of the data correctly. This is a very great tool. So right now on almost all our seismic projects, we definitely will do performance-based design. And performance-based design, basically we can consider the nonlinearity and ductility of structural members. We can use a PBD design to evaluate the overall behavior of the system and each member's behavior. We know exactly what it is. And even the connection details, we know how it works. So at different levels of seismic, we know what it can do. It's different from the pushover. Pushover is something I learned when I was in school. Now with the Abacus final element, we know exactly what we do, and we do all the adjustment. But the thing is, we need to find the right time history curves. In China, we have to go to the seismic expert consultant to get a specific seismic curves. Some of them can be totally not, that will fit the frequency and the character of this building. You don't just take the curves from somebody and say, I'll take it. There's a lot of, we have to try first and see whether it fits your building. So in this job, we use 4 curves, which is a real-time history curve from the real earthquake, and then the other 3 is a synthetic one. And in order to come up with the design that is more foul-proof and more all around for seismic consideration. We do go back to the expert to trace some seismic curve. We found that some of them are totally not applicable for this region. So at the end, we use 7 pairs of seismic curves to come up with that. So it's a Zone 7 in China. For severe earthquake, it's a return period of 2,495 years to be exact. It's a 310 gale, and with 2 to 3% exceedancy in 50 years. So this is a part of the sample we did that. You can see the XY axis we compare because the building is symmetrical. It helps so you can tell after you scale the curve, it comes up with a reasonable result. The link beam are designed to yield, to dissipate energy, the concrete link beam with steel embedment, and the core wall remain elastic during severe earthquake. The natural frequency is quite good. Actually, that's another story. For a 100-story building, I always like to shoot for around 9 seconds or 10 seconds or more, even 11 seconds. Okay, thanks. But on this job, China, they really will not allow us to go for a more flexible building. So fortunately, with the bracing, with the natural mega bracing, we don't have to put up that much fight or that much burden with that. So we have an 8.2, and the torsion is very reasonable at 5 seconds. So it is a very successful job. For 50-year wind deflection, for earthquake, we are up to L over 500. And then wind doesn't control at all because the geometry is a perfect, good example for reducing the wind load. Tapering building and also all the facets is really reducing wind load. Some of the wind load deflection is almost L over 1,000 or better. So you can see how efficient this building has been. Okay. And the owner at the end is extremely happy. We don't need a 2-mast damper. See how comfortable the acceleration is. And it turns out the tonnage is one of the lowest in China for a 100-story building. This is another cross-slot bracing in China, 4-story basement. You know what this umbrella is? They're the hand dug caisson. It's man and husband and wife team. 2 of them are digging this 20-meter deep caisson by hand. And it is about 20 meter deep, 1.8 meter diameter. It belts out to 3.7 meter. Because when you dig, you don't, unless you work with your brother or your relatives, because people get killed down there. So normally they really work with husband or wife and father and son. In China, in southern China, they banned this operation already because it is dangerous. But in China, they're still doing it. But of course, things have improved a lot with all the equipment and things like that. But you can see each umbrella is a hand-dug caisson. We are hoping that it will be built soon. And then I would like to thank all my teammates. So their pictures, they're good looking. And I have to mention the other team architects and the owner and the local East China Design Institute is our local partner. They're doing the CD drawings, taking all the heat, not me. And out there, I take all the credit for the low wind load. Thank you very much.